Okay, sir, I think we start.
Okay.
After that, the people will joining. So, sir, please switch on your video.
Yeah, sure.
Yeah. Yeah. Good afternoon, sir.
Good afternoon.
Yeah. Uh, I welcome. Sir, I am audible to all of you, all professors.
Yes, sir.
Yes, sir.
Professors are there.
Yes. Yes.
Yes. Yes. Very good. Very good, sir. So, good afternoon, all of you, and good afternoon, Mr. Jitesh, sir. I welcome to you in the faculty development program on electric vehicle organized by Mechanical Engineering Department, Veermata Jijabai Technological Institute, Matunga, Mumbai. I welcome you, sir, and we start with this session on simulation of electric vehicle using ANSYS solution by Mr. Jitesh Erancheri, Country Technical Head, LSDYNA. So we start with this session with the small brief introduction of Mr. Jitesh. Mr. Jitesh Erancheri is a country technical head of LSDYNA. He is a specialist on LSDYNA software with an experience over 17 years, with a strong experience in manufacturing process, especially sheet metal forming. He was the focal point for all LSDYNA support, sales and training for most customers across the India. His vast experience of simulation projects are related with manufacturing process. His expertise in LSDYNA application also includes crash worthiness, airbags modeling, seating system simulation, blast modeling, manufacturing process, NVH, bird strike, bird ingestion, blade containment, FBO, ice impact, evacuation system, seating system designs, fuel tank slushing, etc. Drop testing packaging design, assembly line simulation. So I welcome you, sir, and hope all the participants, professors and research scholar will enjoy this session. Thank you, sir.
Thank you, sir. Thank you for this nice introduction. And uh, welcome everyone to my talk. In this session, I'm going to talk about how we can do simulations for electric vehicles using ANSYS solutions. So this is my agenda. Very quickly, I will take you through my company, Kaizen Technologies, couple of slides. Then I will directly go on to ANSYS solutions for electric vehicles. Then an introduction to LSDYNA software, which is again part of ANSYS solutions. And then various ways by which we can simulate vehicle dynamics, suspension systems, and so on. Battery crash, it will be the next topic. Then, of course, the thermal management of the battery, which is called battery cooling, can be also will also be covered. And eventually, I will just give you a summary. What are all the simulations you can do using ANSYS solutions? So quickly about Kaizen Technologies. This is our office in Bangalore. We have predominantly three business units. Our major business comes from engineering solutions. We have been with LSDYNA for several years, and LSDYNA is one of our, I would say, major engineering solution. ANSYS and LSDYNA, they are major engineering solutions what we offer to our customers. We do sales, support, and train engineers and the students and the faculties in these solutions. We also develop CAE products around LSDYNA software. We also have Android applications related to that, and of course do customization basically for process enhancements. We are also having our own electric vehicle and solar vehicle. We have a small R&D for that. We do develop prototypes for. We already have a prototype which works on solar and electric powers. Let's quick highlight. So we started to support LSDYNA technologies, and then quite a lot of domain expertise. My director and myself, close to around 2 decades of LSDYNA experience itself, and then 20 years of working with parent company in the US, which is called as LSTC, which is now part of ANSYS. Technical support team, we have a large technical support team, and then we also have a development team for LSDYNA tools. So we do develop some products around LSDYNA. Offices are here in these locations, and then we're going to have one in Hyderabad soon. Customers, these are a few of our customers. You name it, any OEMs or you name it, aerospace companies, we do support them. We do help them to develop the solutions for basically the simulation models, as well as even method development for those companies to develop their product. Okay, coming to the introduction to ANSYS solutions for EV. Before I start, I just wanted to give you a brief introduction. I would say like brief fundamental information related to the electrification, which is say like there are basically 4 pillars which we call for any EV vehicles, rather any electrification of any of the vehicles. The first is the energy source. It's nothing but the battery. Then comes the power electronics. Then that is going to be your the electronics part, which basically controls the efficient use of the battery. And then we have electric machines, that means nothing but the motors, which is going to be the driver for your vehicle. So, and then finally the mechanics in the sense like everything put together from a structural perspective as well. So how everything works, put everything into one system, and then start integrating. I mean, basically simulating a virtual model, which is basically a something we call as system analysis. So these are the 4 pillars of electrification, and of course, in each and every pillars of this electrification, certainly a simulation can reduce the prototyping in terms of batteries, prototyping in terms of BMS or any of such kind of electronic systems, prototyping in terms of motors, and then of course finally the integration of everything and whether the system is working as expected. And what I'm going to show here is some of the challenges what today the battery technology, rather the battery technology has is they are just looking for something which is of very high performance, at the same time should be safe enough, and the cost has to be reduced. So of course, these are very, very, I would say, steep challenges that this industry is facing, and certainly need a lot of research and development to arrive at these to address these challenges. And that's where one of the important fact that simulation certainly going to help to predict, or rather to reduce the prototyping in each and every scenarios. For example, if you wanted to study the range, or if you wanted to increase the range of a specific rated battery, then you can do the simulations, and then you can test that. And if it is a charging, again, the similar way. And of course, it's a live again. So there are a lot of kind of challenges in terms of the thermal reliability, how much is the temperature coming out of it, and what is the electromagnetic interference, EMI, EMC compliance from the battery. And of course, when it is coming in a structural abuse, like for example, if it is a battery crash, or it could be a nail penetrations, or what is going to be the temperature generated, what is going to be the charge or it could be like, for example, if water goes inside, water ingress simulations. So I mean, water ingress studies and all those things has to be carried out to ensure that such kind of abuses are not being has to be handled properly. And of course, at the end of the day, we need efficiency in terms of overall system, not just as a battery. So overall, the system should work efficiently. At the same time, complying to all those regulations, including the structural abuse and the thermal reliability. How ANSYS helps in these scenarios? ANSYS helps a complete workflow for all the I would say for all those people or the users who are working in this EV vehicles. In the sense, like, it basically gives a multi-scale, multi-domain, and a multi-physics workflows right from the cell to the complete system. How it works? That means we can have to the level of the cells, and then the performance of the electrode and the cells can be predicted. Then moving on to the modules and the thermal management of the modules, like what could be the thermal impact, what could be the temperature generated, and then to the EMI, EMC compliance, and then as a structure, how the battery is going to be reliable, and I mean how the battery structural reliability studies, how it's going to be affecting on various kind of the load cases. It could be an impact, it could be penetrations, it could be something else, many other load cases. And then a battery management system. Battery management system is again another part, a very important part to efficiently use the batteries, and we can simulate that. We can study those, study those things, and then of course the system integration, into it. So that is another aspect of it. Basically, to comply to the AUTOSAR rules, regulations, and so on. Let's go in detail, like right from the cell and electrode performance. Some of the engineering challenges what we have seen is that the sensitivity, the thermal sensitivity of this electrochemistry, and of course the complex structures of the electrodes, the porous electrodes, and of course the degradation of the performance as and when it keeps aging. So ANSYS offers a solution which basically it comes up with a lithium battery template where the users can directly key in those data and then simulate and study the sensitivity of various kind of parameters. It could be the materials, it could be the particle density, or it could be maybe electrode thickness, and so on. You can also study different electrochemistries, and then of course the impact of temperature, and of course the C rating of those cells, and the state of charge versus the VOC versus state of charge curve can be generated without any physical test. So these are some of the I would say some of the outputs one can generate right from the when you are looking from a cell performance. Now let's just say you wanted to study on a battery module and a pack as a thermal management. What could be the temperature generated from there, and then how it is going to be affected. So that's where something where we can study using our conjugate heat transfer solutions. Where we can study the sensitivity of those temperatures, what could be the cell current and the voltage, and of course from each and every cells, how much is it's going to be varied. And we can also study the battery cooling systems, like what could be the right approach to cool this particular battery. It could be liquid cooling or it could be air cooling. And then we can always do different predictor. I would say virtually do testing on different drive cycles. The fundamental thing is we can say the thermal runaway, then study those things, and then try to understand what are all the different kind of abuse responses that needs to be carried out, and then of course that is pretty much important in terms of predicting the failures. ANSYS offers reduced order models, which can run at a fraction of a normal simulations, and then produce thousands of designs in seconds. So that's something which is basically one of the new trends in the simulation industry, where we build the reduced order models and then generate new designs and do sensitivity analysis, and then then arrive at the design different variables that can actually cause issue, I would say, like failures, or what could be the more sensitive variables that can actually affect the performance. EMI-EMC analysis is again another standard process one has to do from our electromagnetic perspective, because electromagnetics has always interference or part of and parcel of it. So we need to study how is the kind of the electromagnetic interference and the compliances for that. So we can detect that using ANSYS solutions for electromagnetics. And then of course you can design, or you can redesign your circuits, or rather you redesign your BMS with those kind of placements of some filters or something like that. So these are some of the capabilities from EMI-EMC perspective, and then comes to the battery structural reliability, where ANSYS mechanical solutions includes which LSDYNA as well now can study various challenges and various virtual testing on various scenarios. Right from the vibrations to the impact, and then of course when the penetrations of the nails and so on, quite a lot. And the beauty over here is it's all coupled. All the physics are coupled. So you have a structural analysis. It's not purely structural analysis. You will also have a thermal analysis with electromagnetic solvers. Getting into that. So ANSYS Mechanical offers the thermomechanical analysis for all those batteries, and then you can also study what's kind of the life in terms of random vibrations and fatigue, and ensure that eventually it ensures that all the abuses are not being catastrophic, like in terms of it should not create a lot of temperature, or it could be it should not. What is the kind of the state of the charge when it is impacted with some bar, or some impactors, or maybe some nail penetrations and so on. Battery management system. This is, I would say, one of the very, very important aspects of EV, and where we need to not only just in terms of using efficient usage of the cells, it also has to have some sort of a functional safety analysis. That means there are some safety standards like ISO 26262, which this is a compliance standard for BMS. It has to be certified, or rather it has to comply this particular standard in terms of the functional safety. And ANSYS has solutions like Medini, which can actually do this kind of analysis, functional safety, and then can actually generate the code for a certified code for that. So BMS is not only just in terms of optimizing efficient usage of your cells, but at the same time it also can be used for. The solutions can be used to predict whether your BMS is complying to the standards. System integrations is the final part of it. That means that we can integrate everything together, working the entire. I would say it's can be called as a digital twin, and the digital twin can be used to have a complete closed loop system where right from the beginning, from the cell to the system can be simulated. With the deformation in the structure. So this is a complete solution. I would say this is a complete connection of the all those things, whatever I was talking all this while. And this basically connects right from the cell to a three-dimensional model, where you would have done some, maybe finite element model to a control systems and to the the battery management system, and then back everything in a closed loop. So this actually gives you a lot of I would say this can be certainly called as a digital twin, and you ensure that your virtual prototype is satisfying its objectives, and then it is pretty much well within the limits and the regulations, and you want to improve it, optimize it. You can do that, and you can just then go for a physical prototyping. So these kind of simulations certainly is going to help any of the designers who are into EV or any of the electric vehicle companies to upfront design a virtual prototype. It can be called, it's a digital twin, and then this can be certainly used and validated anytime, and then before you work into a physical prototype. And then comes to the integration, the introduction to LSDYNA, and this is our the second topic. And then in this, I'm just going to give a brief about LSDYNA software. So LSDYNA was earlier, or rather, I would say LSDYNA was developed at Livermore Software Technology Corporation, Livermore in the United States, and I think 2 years back, ANSYS acquired that company. It has been front runner, I would say, the global leader in terms of the crash analysis. It started with as a software code developed for impact for basically the bomb drop analysis, and then by a nuclear scientist called Dr. John Hallquist in the Livermore National Labs, United States, and somehow it picked up in the automotive industry, and then people in the aerospace industry uses it for bird strike simulations, locomotive industry uses it for rail coach crash simulations, appliances industries uses it for drop analysis, and many other analysis for that matter. And it's since it has been born in defense, and it's been very widely used for blast, bullet penetrations, ballistic impacts, and then internal ballistics, and so on. Construction equipment industries uses it for rollover protection systems. Biomedical industries uses it for artificial wall, for tissue modeling and simulations. And then various other industries uses it for various applications, like shipbuilding uses it for ship collisions or underwater blast, and so on. So these products basically come with multiple other ones. It's called as LST product. After ANSYS acquisition, it is called as LST. And then LST products includes LS pre-post. It is a preprocessor where we import the CAD model and then do the mesh generation, apply the loads and boundary conditions, and then that's what. And then of course, when you run it in LSDYNA solver, and then take the results and then post-process it. LST products also include LS-opt and LS-task. These are the two, I would say, optimizers which comes along with LSDYNA. LS-opt is used for various sort of optimizations in terms of thickness optimizations, in terms of parameter, I would say, material parameter optimizations. It can be used even with your EV models for various optimizers in terms of whatever the design variables what you have. Dummies, barriers, and tires. These are the three FE models which comes also along with LST models, LST product, LSDYNA. Basically, a calibrated dummy models which can be used for the crash analysis. As you can see on the screen, that the center one, you can see a CFD simulation, then you can see the second one as an airbag, and then the third you can see as a metal forming simulation. So everything is in one single code, which can do, I mean, though it is multiple physics, everything can be done in one single code. And that's one of the reasons why LSDYNA is very popular, because it's explicit to implicit at any given point of time. the form part, and you do a forming analysis in explicit, and then at the end of the simulation, you wanted to do a spring back studies, then that can be done in implicit without manual intervention. Heat transfer is another analysis where we have a thermal solver, which basically works with our structural solver as well. So we can have a coupled heat transfer analysis or even completely thermal analysis as well. ALE, mesh-free methods, these are all of the trademark, I would say, use of LSDYNA, where they use it for fuel tank sloshings or even the bird strike impact and so on. Acoustics and frequency response are also the capabilities of LSDYNA, where we can see exterior noise, interior noise, and so on quite a lot. The discrete element models. The discrete element models are the ones where we can study the interaction between the particles. Where for example, you wanted to study soil structural interactions, or you wanted to study some sort of a, for example, you wanted to study when the vehicle goes over like a sand or a soil, how it's going to happen. So this kind of studies can be done in a discrete element. Compressible flow solvers are also available, and incompressible flow solvers are also available along with electromagnetics, which I'm going to talk a bit detailed in this coming slides. So that's what, it's one single code with multiple physics. Let's get on to the vehicle dynamics part, and then vehicle dynamics part is also very important in terms of the vehicle development program. So as you know that this LSDYNA comes from ANSYS family. I just thought I should take some time to introduce you to a product which is called as ANSYS Motion, which is very effective. I would say very extensively can be used for all the kind of a rigid body analysis. So this is something which as you can see it in the screen, that various sort of the kinematic simulations can be calculated, can be modeled. All you need to do is just import the geometry, and then from these simulation models are being built, and then it will be solved, and then it can be I would say you can extract the joint forces and so on. So as you can see here, we have a complex gears with a lot of contacts, and then everything can be handled. And you can see there are a lot of chain sprocket systems, then the cylinders and the pistons, then of course the cars. And you can see the cornering of the cars, and then then you can see the stabilities. You can predict those things in ANSYS Motion. And at this last, what I wanted to show here is about the simulations where you can have the transient simulation where the stress values also can be predicted. So that's how it is. I'm just wanted to show. It's not just a rigid body dynamics. It can also bring in flex bodies into picture, and then simulate all the kind of scenarios, all the kind of the kinematic simulations. The suspension systems can be certainly modeled. There can be you can just bring in those CAD models, and then introduce this suspension system. This is a two-post simulator, and then you can see that those struts, arms, and everything can be simulated. You can extract the joint forces, and then predict it. So there are a lot of kind of joints available here, constant velocity joints of the fixed plunging, and then there are many joints available. So you can actually use those joint libraries, then model these things, and then then simulate in ANSYS Motion. As you can see here, we can also do some sort of the joint simulations in terms of the bearings, and then you can study the deformation or the flex bodies in terms of the kinematic simulations. Life predictions. Life prediction is another important aspects in ANSYS Motion, in the sense you can actually not only simulate the flex bodies and predict the stresses, but you can actually use them to to predict the life of it. So you can see here, like there are different angles of rotations, and then you can see here like you can study these things and then study what's the max value of the stresses which has been built at what particular angle you are getting these stresses, and you can study the failures. And the failures you can see here exactly over at this particular locations where the failures are seen. So so it can reproduce the real life problems in terms of the fatigue analysis, and then that will be pretty much useful from overall product design perspective. ANSYS motion helps users to build these assemblies very quickly, in the sense like we have a shaft designer's template where you can directly define the shaft. We also have a housing designer template. You can design the housings, and then there are gear designers to design the gears. You can just define those gears and the all those parameters for that. And then there's certainly a bearing designer. So the bearing designers certainly can be used to model the bearings as well. So there are a lot of toolkits which comes along with ANSYS motion, rather which can be added to the ANSYS motion. And then with that, you can have a comprehensive simulation of your entire system. And just to let you know that these simulations can also talk to the 1D simulations, if you or rather we call it as model-based system engineering MBSE models. For example, Modelica libraries or even ANSYS Twin Builder. You can just connect with them and then build your hydraulic systems. For example, you have some hydraulics needs to be optimized based on your kinematics. You can just connect them with the hydraulics to the hydraulics, which you can build it in your ANSYS Twin Builder, or it could be a Modelica libraries or whatever it is. And then you just connect ANSYS motion with that. So every single movement of ANSYS, or every single calculations of ANSYS motion will be data will be interchanged between ANSYS Twin Builder or a Modelica libraries or whatever the 1D MBSE tools where you use it. So it's not only just stops at the kinematic simulations or at the flex bodies. It can certainly do a co-simulations with 1D solutions. Now, coming to the aspects of the kinematics. So the kinematics is so the kinematics is pretty much important. I would say that the models are certainly going to be accurate only when you capture your road excitations properly. That means, for example, you have you can do a kinematic simulation of a car, for example, a lane changing simulations or a cornering simulations in a kinematic solver. But the excitations from the road, or rather we call it as when you do a proving ground testing. So all this kind of testings are called as proving ground testing. So when we do a proving ground testing, the excitations to the car are coming from the road. So in the roads, if the excitations are basically transferred directly from through the tires. So if you do not have a proper tire model, your excitations to the car body is going to be completely different, and it's going to have a different load excitations which is going to be generated into the car. So it is very, very important to have a proper tire model for any vehicle level kinematics simulations. It could be a proving ground simulations. For any of the proving ground simulations, you need to have a good tire models. And that is one of the reasons why LSDYNA's tire models are very, very famous in terms of using it for any of the proving ground simulations. So LSDYNA tire models has a detailed models which has been benchmarked, I would say, validated at Michelin. Michelin tire models, and then you can see that we have when I cut across this models, just wanted to show you. I put a picture over here that you can see, they can see wire belt bottom, sub thread, thread, then belt overlay, side walls, and all those things have been well captured in this model. So these models will give, if you introduce this model into your vehicle, and then it's going to have a good excitation capturing, and then that's certainly going to have a good effect on your well-strung durabilities and so on. So I just want to show you a few of the examples what we can. So this is something like, with LSDYNA tire models, we can digitize the roads. This is called the proving ground testing, where you can actually do the contact. It's a good contact between the tires, and the tires are deformable. And the earlier one, kinematic simulations, what we have seen, the tires are rigid. So you can the excitations is going to be different when you introduce tires as a deformable, and LSDYNA offers a lot of materials to model a very accurate tires. So you can see here, like the joints, there can be stress. And these stress plots were basically used, and then you can actually calculate the spot weld fatigue, because all these assemblies are, there could be joints on the A-pillar joint, then you have B-pillar joint. So there can be a lot of stress concentrations coming when it is going over various terrains, and these stress concentrations can be captured, and then eventually their failures can be considered for here. Yeah. Another example over here is with the chassis. This is another example, like you can study these things, such kind of modeling, such kind of motions with the different road surfaces, digitized road surfaces, where you can actually do the simulation with the actual deformable tires, and then the excitations onto the structures are going to be precisely the same as actual. And then this is another lane changing simulations by Kia Motors, and they have used LSDYNA software and to study it. So the beauty here is, like, only one model needs to be built. You don't need to have multiple models for all this kind of analysis. Just you have one model. The same model can be used for battery crash. The same model can be used for vehicle crash. The same model can be used for vehicle lane changing. The same model can be used for NVH and so on. Coming to the battery crash, LSDYNA's EM solver has been developed, I would say probably 2007 or 6, not 7, I think, it's been introduced into LSDYNA. And this particular solver can do quite a lot of stuff. It's been developed over a period of time, and it can do, so initially it started with, it's been developed as a partnership with Ohio State University for electromagnetic forming. Then there was a requirement from various other manufacturing processes like resistive heating and spot welding, and then induction heating. So all these things were the initial requirements from the customers. And then the battery crash and thermal management came in picture. Then now it's also widely used in the medical industry for electropsychology and cardiac simulations. It can also be used for electrostatics, and then this is the kind of EM solver capability. Now, how in LSDYNA the true multiphysics works? The multiphysics works is pretty easy. That means that the electromagnetic solvers can talk to the thermal solvers, and the thermal solvers can also talk to the solid mechanics solver. And then we also have the ICFD, which certainly has a direct connect with the electromagnetic solver. So, if you look at this, the entire electromagnetic solver capabilities has been coupled very seamlessly with these other solvers of LSDYNA. So it's called as the thermal solver can transfer the temperature, electromagnetic solver can compute the joule heating and give it back to the thermal solver, And this Joule heating temperature data will be passed on to the solid mechanics solver, and the solid mechanics solver will calculate the deformations based on the temperature what has been given, and then it will give it back to this thermal solver. So that's how it works. It interchanges the data, and then similar way, the electromagnetic solver will calculate the Lorentz forces, and which will give to the solid mechanical solver, and the solid mechanical solver gives the displacement back to the electromagnetic solver. So it's just exchange the informations between them. And in the ICFD solver, it's a CFD solver from LSDYNA that can be also been coupled with the thermal solver, and you can just have a connection with them. So they also do interchange the temperature data from this is a conjugate heat transfer methodology. So that's what in the battery model, this is like it is. So the mechanical solver will pass the displacement informations to the electrical solver, and electrical solver will pass the informations of the temperature to the thermal solver, and the Joule heating, the Joule heating data of to the thermal solver. And that input will be taken by the temperature, and that will be input by thermal solver and then given back as the temperature data. So it just chalks each other and simulates the battery problems. In LSDYNA, we can simulate batteries in 4 different models. So the very fundamental, I would say, the very old models was, I would say, the very initial level when it was first introduced. We used to model it as solid elements. That means something about cells, with solid cells, hexahedron mesh. And it will be layered meshing. It was there already in LS Prepost, so we use that LS Prepost to model the layered mesh. And the same mesh is used for electromagnetic solver, thermal solver, and mechanical solver. So the thing is about the element formulations, and then that has some of the settings needs to be done. So, but of course the computation time is going to be really huge, because you need to model a lot of cells if you have a big battery pack setup. So that is one of the reasons why then we introduced composite T shells. That means it can be modeled with composites, that you can just model as one single solid the T shell, and this basically means that this is basically connected with the Randall circuits between those T shells. So it is more accurate, and detailed deformations can be done. It is faster in runs because the number of elements are less, and then it's have a larger time step, because when most of the problems what we talk about when you are using LSDYNA are all explicit. So the element sizes certainly going to be having an impact on the solution time. Then we have the battery macro module, macro model, which is called as BATMAC. And the BATMAC model is it's one of the newly introduced one, and it can do everything with few solid elements. That means you can start building the batteries entire thing with one single set of solid elements. So there is no need to have layered modelings, and there is no need to have much of the complexity what you were seeing in the initial models. So there are 2 fields at each node. One is positive and the negative collectors, but that's how basically it works, and that's how your mesh has to be generated. The last one, the 4th model, is recently introduced, which is called as a meshless model. That means that we basically use one single circuit for the whole cell. I mean, it's kind of a meshless model where very quick. It's a lumped model which can actually generate the equivalent Randall circuit for that entire cell. Now, how do we simulate this? So, for example, if you have some sort of a impact, and this is something we a case study from Ford Motor Company. Basically, what they're trying to see here is they wanted to study the short circuit resistance when you have a external short circuit. How the temperature profile is going to be generated. So you can see here when it have external short circuit, you can see on the battery pack. You can see the temperatures start increasing from it's from the external, and it is just keep going inside. And this is how the experiment versus and the simulation. So it's very close matching with the actual. And this is again another example of external short circuit. But this time, what happens is here we use meshless method, so there is much more faster, and you can see the temperature behavior as well. So you can see here the temperature increased, and then of course when you have external short circuit, it's going to affect the temperatures. This is again another external short circuit, but this time it is more towards because of the ball impact. So, so when you have an external, so this is one which is having with the rod, a conducting rod, which is acting at the terminals, and you can see the external short circuit over here. So you can see the temperature, generated into the cell when an impact of this rod is happening over here. And when it is an internal short circuit, you can see here the ball comes and impacts, and then you can see here the kind of the temperature profiles. This is again another example of a internal short circuit where the wall is impacting by a battery pack, and there's rigid wall impacts, and then what is the kind of the current density and the temperature. Another test one has to do for the simulation, or rather the I would say for the validation or the regulation purpose, is about the nail penetration. That means you need to do is study on the nail penetrations and see what is the kind of the short circuits and the temperature results. What is going to be temperature profiles when the nail is impacting a battery pack. So in this case, we have close to around 30 cells, and then you can say there is a nail which is getting penetrated, and it is creating holes into this battery pack, and you can see that temperature is getting elevated slowly. So you can just see that because it is thermal analysis, it's slower. So you can see that the temperature is getting elevated over here. Okay, so here the thing is we have used the BATMAC module for the first 10 cells, and then the meshless method for the rest. So the first 10 cells is what basically we are showing it as fringing it, but the rest of the things can also be fringed and generate the temperature on that as well. Then the important thing is about the thermal management. The thermal management of those batteries are equally important at the same time the same as the case with your the battery crash, or the battery the nail penetrations and so on. So there is a pack of 96 cylindrically cooled cells, and then we just wanted to study using direct air cooling or the liquid cooling. So if you see here, this is from our ICFD solver, LSDYNA's ICFD solver. You can say that there is no cooling. The temperature is going to be at 43 degrees Celsius. This is something which is without any cooling. Now, when you are cooling it with by glycol, you can see the temperature reduced, and then it is just after some time it is just slightly increased, but it comes around and it just goes down up to 20 23 or something like that, going down, and then finally it reaches up to 24, 25. Now this is at by glycol at 20 degrees Celsius, and then you can see here that with This is air cooling at 20 degrees Celsius, only air cooling. And then you can see it's getting at 25 degrees Celsius, 25.8. And with air and the liquid cooling together, you can get 23.4 degrees Celsius. So what I'm trying to tell here is like, so we have here the batteries are modeled as electromagnetic. Batteries are modeled using our EM solver, the electromagnetic solver from LSDYNA. The flow or the cooling simulations have been done from the ICFD solver of LSDYNA. And even with the same mesh, you can do a battery crash. So only one model needs to be built and one model needs to be solved. So there is no need to have multiple solvers, multiple solvers or multiple softwares to be added. Everything can be done in one single software. That's the beauty of LSDYNA, and that's why people say it's just a single, one code, multiple physics solution. So that is one aspect of it, and then let's just another simulation. What we are going to talk about now here is the water ingress. So here also the simulation starts like this. Like we have some terminals here, and these terminals have been modeled over here, and then there's a water. And then let's see how it, when the water goes over it, you can see there is a state of charge reductions in here. So you can see this is the state of charge, this curve, it's just gone down, right? Just gone down. So the point I want to make here is the current, basically the thing is like you can simulate multiple, not only just the water, not only the cooling simulation, you can do the water ingress simulation also in the battery module during your vehicle development process using LSDYNA. So LSDYNA summary gives like this when the EM solvers. So EM solver has solid elements based models, battery models, composite T-shells based battery models, macro models, and meshless models. So if the cell geometry is pouch, cylinder, or a prism, the solid will work, but if the meshless model will not work. And then if the cell is a detailed study, then you cannot use macro models or meshless models. You may have to use solid models, the composite models. If it is module is small, then you can use solid elements. If it is otherwise, if you can use composite T-shells. Battery pack, then that is basically much better to do it in these two models, not in these two. It takes a lot of time. And then connection to external circuit, it's possible in all the things. Internal short circuit can be done in everything, but cannot do it in here. External short circuit can be done in all those approaches. Joule heating can be done here, but here is an average of all those cells. So here it's not at all possible, and mechanics also is not possible over here. Exothermic reactions that can be calculated from here in all those three. So this is very fast, but it has some limitations. This is the next fast. This is the next one, and this is the slowest, and this is the next slowest, and this is the most slowest but more accurate here in this. Of course, it takes a lot of computation time. Yeah, so the conclusion here is ANSYS offers all the EV electrification process. I would say the R&D process, a performance which basically close to around 1,000 times. That means with the reduced order models. That means you just need to have only few designs to be done, and the balance everything is been been generated from a trained data, which is from a machine learning process. So ANSYS has this reduced order models, which basically enhance the product development cycle, because you get 1,000 designs in 1,000 seconds. So 1,000 responses from 1,000 seconds. So once you have the data ready for let's say, for example, few of those iterations, then everything is just matter of few seconds. And you just imagine when one iteration takes let's say 5 hours or 6 hours, when you're talking about seconds, where you can actually generate this data. That's the beauty of reduced order models, and ANSYS has that. ANSYS has that capability to introduce it, so you can do a lot of sensitivity studies and then arrive at the right parameters that basically contributes to the better performance of your EV system. Design cycle can be reduced to 50%. So that is what here it's been telling, like the EV, because of all these kind of new techniques coming into the simulation industry, especially with ANSYS, we can reduce this design cycle to close to around 50%, and the productivity gains, or rather the cost reductions can be close to around 30%. So this is the kind of the advantage the user will get when they use ANSYS for the simulations, because this is the only, I would say, the tool which has everything incorporated inside. You have an explicit, you have an implicit, you have electromagnetic solvers, you have electrical solutions, you have solutions like IcePack, which can actually calculate what is the kind of the temperature distribution from each and every cells in a battery. For example, if a chip is running at a specific hertz frequency and it is producing so much of heat, you can actually predict that how should be your cooling, so the cooling system to be introduced into for that PCB, so that it takes out most of the heat out. So it has a comprehensive solutions for EV vehicles, right from cell to the system. And to the last slide of this my presentation. So these are the products what ANSYS solutions these are the applications where ANSYS solutions can be used. So if you are using a cell or electrode performance, then of course you may have to go with the Fluent or ANSYS LSDYNA mechanical and twin builder. If you wanted to have a module or a pack thermal management, it's always better to have a Fluent and a twin builder. EMI, EMC can be done with ANSYS twin builder, and then the battery structure reliability can be done with ANSYS mechanical and LSDYNA softwares. Then we have the battery management system, where we need to have ANSYS Medini. It's pretty much important because this has a safety codes which can be generated from there, and that is very, very mandatory as per the regulations. So Medini with Fluent and ANSYS CADE with a twin builder could be the right option for BMS. And system integration, that is a digital twin. It's pretty important when you have all these things done. So where you can make a virtual prototype for functional prototype, and that can be done using. You can use all ANSYS Fluent or twin builder and so on. So that's it from my side. If you have any questions, you can ask me. I can try to answer you as much as possible I can.
Yes, sir. Thank you very much.
Welcome.
Yeah. Thank you for the nice presentation. Now I welcome all participants for if any query, please ask to the sir. Related any simulations, modeling. Okay. Thank you very much, sir, for the nice session.
Thank you. Thanks everyone for listening to me, and then thank VJTI for giving us an opportunity for presenting ANSYS solutions.
Yes. Thank you, sir.
Thank you.
Yeah, you can do, sir.
Thank you very much.
Please submit the attendance. And sir, tomorrow at the end of the session, last session, we have an examination test. Okay, it's a compulsory test for all of you. Okay, sir?
Yes, sir.
Yeah. Okay, sir. See you tomorrow morning at 10 a.m. Till that, bye bye. Have a good day.
Bye.